Number 20 is on carbohydrates, which you learned between exam 3 and the final. So they're asking you to take this Fisher projection and turn it into a chair conformation. And the rules for translating Fisher to chair conformation are the same as the rules for translating to the Haworth projection. The only other trick to this question is they give you radio-labeled oxygen over here. Forgot to write the hydrogen. And all that means is they want to make sure you know where this oxygen is and what it does when you go to that ring. Now remember, this is the second to last OH. And that is the oxygen that forms the ring. It's the one that uses its electrons to attack the carbon of the CHO, which is an aldehyde. That would swing up like that. So whatever ring you draw, the oxygen that is inside the ring will always be this penultimate oxygen, the oxygen that is second from the bottom. Now let's see what size ring we would make if we did that. 1, 2, 3, 4, 5, 6. So we'll number that accordingly. 1, 2, 3, 4, 5, and then the oxygen is 6 because it's making the ring. So start by just drawing the generic form of a chair conformation. Okay, that pinched in bow tie. And now all the answer choices put the oxygen in this corner, so I'm going to try and match that. And now based on my numbering, I said this was 6, 5, 4, 3, 2, 1. Now let's see. Carbon 1 is our anomeric carbon, which means the OH on that will be a squiggly line. We don't know whether it's up or down, but looking at your answer choices, they drew every single one of those anomeric OHs pointing up. So I'm just going to draw it to match that. But again, there's no real, since this question doesn't say anything about alpha or beta sugars, you don't really know whether that OH should be up or down. They just limited your option based on the answer choices. Now we have to figure out 2, 3, and 4 stereochemistry. So we were seeing before in the previous question, when you have a Fisher projection and your OH is on the right, that means when you translate that to the Haworth of the chair, that OH will point down. And on the other hand, if the OH is on the left side of the Fisher, that OH will point up. So let's look at this. Carbon 2 has an OH to the right. If it's on the right in the chair or the Haworth, the OH points down. So in this case, the OH would point down like that. Now carbon 3 has an OH on the left. And that means the OH should point up in the chair conformation. Carbon 4 has an OH on the right, which means that OH will also point down. And finally, carbon 5, well, carbon 5's OH is in the ring right now, that's our O18. So carbon 5, your penultimate carbon, you have that other rule because it's the CH2OH that comes off of that. And the rule is, if the carbon 5 in the Fisher projection, if its OH is on the right, when you draw your chair or your Haworth, the CH2OH points up. And in the Fisher, if the OH is on the left, the CH2OH will point down. So I'll start this one so you can say it matches up with that. Draw a square there. Okay. So if you're looking at your penultimate OH in the Fisher, if it's on the right, the CH2OH in your chair or your Haworth will point up. And if the OH on your Fisher on that penultimate carbon is on the left, the CH2OH will point down. In this structure, the OH is on the right, which means the CH2OH should be pointing up on that Haworth, like so. And so that is the structure of your answer, and so we need to find the answer that has an OH pointing up, an OH pointing down, an OH pointing up, an OH pointing down, and the CH2OH pointing up. And the only one that matches that is choice B. Of course, that also not forgetting that the oxygen in the ring should be your radio-labeled O18. So any choice that doesn't have that can be automatically ruled out. And as it turns out, every choice except for B, so you didn't even have to do the stereochemistry on this. If you look at your answer choices, only B has the radio-labeled oxygen in the right position. So, wow, that's a lot of work for nothing. Anyway, that's the gist of this question.